Okay, here's a question involving absolute values. We've got an equation 2x plus 4 absolute value equals a times absolute value of x plus p plus q. And it says that it's satisfied for all x is an element of negative 2, 1. So what that means is that the solution to this equation is really a range of values, anywhere from x is negative 2 up to positive 1 inclusive. So these square brackets means we're including the negative 2 and the 1. If it was a curved bracket, it wouldn't be inclusive of the negative 2 and 1. So in other words, our solution set, if you like, is x is anywhere between negative 2 up to positive 1. So what we're trying to find is these values a, p and q such that this equation will give this solution range of values. Now what we can do with a question like this is think of it graphically. Think of the left hand side. We could graph the left hand side of that equation as y is equal to 2x plus 4 absolute value, and the right hand side of the equation y is equal to a x plus p plus q, and the intersection of these two graphs will be between all the values between negative 2 and 1, and we're trying to find the values of a, p and q that give that solution set. Now I guess the sort of trick with this question is first of all, this can be quite easily graphed, so we can graph that easily. And then we're trying to find these values of a, p and q such that the graph of this function will overlay this graph in those values only. Now what you'll notice about this function is it looks somewhat like the old quadratic transformations function. Y is equal to a, x take p all squared plus q. Got your dilation in the y direction, scale factor a, horizontal translation of p units, and moving up, translating up by q units. So we can use transformations perhaps to get our solution. So if we have a look, we can do this fairly easily on the class pad. So if we have a look first of all at the graph of y is equal to 2x plus 4, so I'll just pull up the graph and drag that little one in there. Okay. Also you might just want to go zoom, initialize. That'll bring it up with that nice screen there that's kind of easy to use for this particular question. But you might want to play around with that screen size just to fit everything on. So you can see with y is equal to 2x plus 4, it's just very similar to the graph of y is equal to 2x plus 4 without the absolute value signs, except that when it hits the x-intercept, the function will be multiplied by negative 1. So instead of continuing on down this way, it flips up, sort of reflects across the x-axis like that. So in terms of transformations, what we might consider is having a look at, to begin with, y is equal to the absolute value of x, see what that looks like, and then see how we can transform that graph so that it overlays our absolute value of 2x plus 4 in the correct range of x values. So next step, we'll have a look at just graphing y is equal to absolute value of x, which again, I'll just bring up the keyboard. There's our absolute value. Oops, what do we want here? Get rid of the keyboard, we'll click in the main screen, then bring up the keyboard, and we'll put in y is equal to absolute value of x. Go back to my graph, and we'll go drag that one on there as well. There we go. So we can see there's our absolute value of x, and we're going to try and transform that so that it overlays the graph of y is equal to absolute value of 2x plus 4 between x is negative 2 and y is positive 1. Now straight away you can see that our red graph there's got the wrong gradient, so we could perhaps fix that up by just putting a 2 in front there, dragging that on there and see what happens. Okay, so we've got the same gradient, and we can see now if we transformed across it would overlay, but it would overlay perfectly. We don't want that. We only want the solution set to be between negative 2 and positive 1. Okay, I'm getting a few too many graphs there, so let's just clear those. We'll put this one back on, and perhaps if we just put that one on as well. There it is there. So what we can see to get our graphs matching just across there, if we reflected the red graph about the x-axis and then translated it, we should hopefully be able to match it up. So really, when we reflect about the x-axis, we then want this critical point here, I guess, to move up 6 units and across 1, so it just matches at that point. So doing that, if we move the graph, or first of all reflect it about the x-axis, that will be putting a negative in front of it. And then if we move it 1 unit to the right, -1, and then add 6 to it, and pop that in there. Just move that down a bit. We can now see that it's overlaying perfectly with the original blue graph here between x is -2 and x is +1. So there's our equation we're after those transformations. So we have y is equal to -2 x take 1 plus 6, which gives us our solutions of a equals -2, p equals -1, and q equals 6. But I guess the key with the question was, considering this in terms of transformations to match it to the other graph in the range of values of x for which the solution is required.